Okay, so this is going to be one of our last lectures for this class, and this is going to be our last chapter. So this is for chapter 12. Now, chapter 12 really builds off of what we covered in chapter 11. And so we're just going to do a little bit of a review to start us off. These are questions that we had last week, so you've already worked on them, and then we're going to go over the answers. So in this first problem, they're talking about the dipole moments of acetonitrile and methyl iodide. Now, if they are giving us dipole moments that aren't equal to 0, then that means that these molecules both must be polar. Now, if they're polar, then it gives us an idea about which one should be more polar. So if the larger your dipole moment, the more polar you are. So in this case, our acetonitrile is going to be more polar than our methyl iodide. That means that as those parts increase, we should be able to anticipate which one would have greater dipole-dipole attractions. So part A is asking us which one has greater ones, and so that should be our acetonitrile because it's got a larger dipole moment. When it's asking us about London dispersion attractions, then we need to think about, well, what drives our London dispersions? And that's going to be our molar mass. So now we have to determine which one has a higher, lower, or molar mass. So in this case, CH3CN has a molar mass of 41 grams per mole. CH3I has a molar mass of 142 grams per mole. And so CH3I is going to have more London forces. So even though it has less dipole forces, it can still have more London forces because London forces is about molar mass, not about polarity. Dipole forces are about polarity. And so now it gives us our boiling points. It tells us that CH3CN boils at 354.8 K, CH3I boils at 315.6 K. And so it wants to know which one has greater attractive or overall attractive forces. And remember that boiling point increases as attractive forces or intermolecular forces increase. So in this case, CH3CN should be greater overall attractive forces than our CH3I. That tells us that our dipole-dipole force, the stronger dipole-dipole of CH3CN, matters more than the stronger London forces of the CH3I. If those London forces were the stronger force, then CH3I would have the higher boiling point. But for us, it doesn't. It's not true. Instead, it's the CH3CN, which has higher boiling point and therefore stronger attractive forces. And so there's a little bit more about that in here. The next one that we're going to look at is we're going to look at barium chloride, H2, CO, HF, and Ne, and we're going to put them in order of our boiling points. And so what I would recommend is go through and identify what type of intermolecular forces or what type of forces are holding your molecules together, and then we can start to classify them from there. So BaCl2, this one is going to be an ionic one. H2 is nonpolar covalent. CO is going to be polar. HF is going to be polar. Ne is going to be nonpolar. So if we think about it, our ionic one is going to be formed by those crystal structure rules. So we're looking for smaller size and higher charges to be stronger ionic bonds. Nonpolar ones, these are all of our London forces, and so this should be about our molar mass. And then when we look at our polar ones, we also want to think about, is there any special kind of polar bonds that we might have to worry about, such as HF being our hydrogen bond. So when we start to list this out, well, we know BaCl2 should be our highest boiling point because it's got the strongest force, those ionic bonds. Because those aren't even like intermolecular forces, they're really more like our covalent bond. So they form really strong connections. From there, we have our next options, which should be our polar molecules. And so we're trying to compare carbon monoxide versus HF, hydrofluoric acid. And so we should have HF next because it's doing a hydrogen bond. And the hydrogen bond should be stronger and therefore higher boiling point than our dipole-dipole. And so carbon monoxide can be after that. And now we have two other molecules. We have hydrogen gas and neon, and both of those are held together by London forces. And so we should put neon next because it's got a higher molar mass than H2. And that's how we can kind of come up with our list. Looking over here, it's a drawn out structure of a compound. And so we want to find out which one has a melting point of 35 degrees Celsius and which one has a melting point of 78 degrees Celsius. And so we're looking at their forces. So if we look at it, they're actually all made up of the same amount of stuff. We have 1, 2, 3, 4, 5, 6 hydrogens. We have 2 carbons and 1 oxygen. So that means that the London forces are going to be equal. We could try to compare their dipoles. We know that this one's got some force going this way. This one's got some force going down. But that might be a little bit tricky to tell whether which one has a stronger dipole than the other. But there's another way that we can tell. And that's this. This is a hydrogen bond. Right? We have a hydrogen directly connected to oxygen, nitrogen, or fluorine. And that's going to be what really separates us apart. So this compound should be our 78 degrees, and this one should be our 35 because of that hydrogen bond. The higher the melting point, or then the stronger the intermolecular forces, and so the hydrogen bond gives it that extra strength. So that's a review from last time. Now we talked about a fourth force ion dipole, but we haven't really used it too much because we've been talking about just our single materials, our pure substances. This chapter, we're going to start getting into our mixture. And so that's going to be when these type of intermolecular forces come up. So chapter 12 is about solutions. And so solutions are used to describe like a homogeneous mixture. And so what we want to do is we want to make sure that for our solutions, we should be able to talk about them in several ways. We should be able to talk about what it means in terms of solvent, solute. We should understand the energies and intermolecular attractions associated with creating a solution. We need to know what entropy is and how entropy can be used to form a solution. And then the last part is we want to make sure that we know how the temperature and pressure affects the solubility of our gases and our solids. Now, from there's also a lot of calculations that come with chapter 12. We need to be able to calculate a given volume of a solution for a specific molar concentration. Use those molar concentrations to calculate things like molarities or how much material we would need to mix with the other one. We should know mass percents. We should be able to do some stoichiometry using solutions. So instead of starting from our grams and going into our moles, we might start from a volume and use our solution to go into moles. We should have an understanding of about vapor pressure and how that's related to our boiling point, or sorry, our temperature. And then we should be able to talk about our vapor pressure, how it lowers, or freezing point depression, or boiling point elevation, all within these things called colligative properties. And then we should understand solubility in the sense that, like, why does a soap molecule work? Because of this like dissolving like. So the first thing we talk about is solubility. So solubility is when one substance dissolves inside of another. And so there's a couple of terms there. The smaller material is called our solute. The larger material is going to be called our solvent. So when we talk about things being soluble, we're talking about that smaller one dissolving into that larger amount of material. That doesn't mean that all things are soluble in all solvents, but there is a range there of solubility. So when something doesn't dissolve, we call it insoluble. And solubility kind of depends on two things. It depends on the types of intermolecular forces, which is that like dissolves like situation. And then there's a second part, which is that we prefer mixing. And so we'll talk about that a little bit later. This push is our entropy. And so we'll look at the entropy-driven reactions later on today. So for a solution is described as a homogeneous mixture of two or more substances. Now, that could be a liquid and a liquid, it could be a liquid and a solid, it could be a gas and a liquid, right? There's a lot of different options for our solution. Pretty much if our material is a homogeneous mixture, you can define it as a solution, though primarily we talk about solutions more with our liquids and solids. You can see up here in this top right, we kind of have our solution forming. The solute is going to be the yellow part because there's not as many of them. The solvent is going to be all that blue. And you can see that when they spread out and they move around in there, then that's when it's a solution. And so that's it going through that dissolution process. So if we put sugar into water, then water is going to be the solvent and sugar is going to be the solute. This is true as long as water is the larger amount. Now, if we put a lot of sugar in there, so much sugar that eventually the sugar becomes more than 50% of the solution, which would be a really, really sweet drink, then our water is no longer going to be the solvent. If we're larger amount of sugar in there, so if we're over 50% for sugar, then that means our water is going to become our solute because it's going to be the smaller amount. And so we can have different types of them. We can have a solid, a liquid solid, kind of the sugar dissolved in water. We can have liquid liquid. That's an example of that is vinegar. That's acetic acid, which is a liquid mixed with water, which is another liquid. And so that dissolves and separates, and we have an equal ratio of them. You can also have a solid solid, which is a metal alloy. You can have a gas with a liquid or a gas with a solid as well. Any type of homogeneous mixture, but these are the three most common ones. So go through and try to classify these as being solutions or whether or not they are a heterogeneous mixture instead. A cup of instant coffee should be a solution. If we make it well, it's going to be homogeneous throughout. Chicken vegetable soup is definitely heterogeneous. You can see that chicken, the vegetables, right? They're not all together. Unfiltered blood is actually a heterogeneous mixture as well. It's a little bit harder to have known that because when we first look at blood, it seems all the same. But when you look at it, you can separate out into different parts like the plasma, the red blood cells. And so there's a lot of different things inside of that blood. I just wanted to include that one because your book seems to talk about it. And so I wanted to make sure that you were familiar with what that is. And then a chromium plated steel bumper is going to be heterogeneous because the chromium is only there on the surface of the bumper. Right? It's plated on top. Steel by itself is actually a mixture of iron with carbons and different other trace minerals, and that would probably be considered an alloy or a solution for the steel only, as long as it's well made and evenly mixed throughout. Now, when things dissolve, we can get two options. We can get dissolution and we can get disassociation. So dissolution of an ionic salt means that our water is going to go in, or sorry, our solvent is going to interact with this solute, and we're going to get our materials to be separated. So dissolution, this occurs anytime anything dissolves. So dissolution is for all processes. And what happens is that it involves three steps. First, the solute needs to be separated from itself. Now, for ionic compounds or our electrolytes, that means that they're going to break into free ions from the crystal lattice. For other compounds, that just means that they are going to break away as molecules from each other. So when sugar dissolves in water, then the sugar molecules separate from the other sugar molecules. The second aspect of that is the solvent needs to separate. The solvent has an intermolecular force that's holding it together. The water molecules like to be next to other water molecules. And so in order for us to make space for these dissolution particles, right, for the solute, we have to break them apart. So we have to move them away from each other. And then our last step is going to be solvation. And solvation is going to be when our solute starts to interact with our solvent to form these new intermolecular forces. And so all of this occurs when our salt starts to dissolve. So whenever we are dissolving, then we're doing all three of these steps. Now, disassociation is specific. Disassociation is only for electrolytes. Disassociation is when we split into ions. So instead of those molecules staying connected, such as our sugar ones where they separate from other sugar molecules, these electrolytes, they split into positive ions and negative ions as they dissolve. So that's our disassociation. It doesn't occur with molecular substances that dissolve without disassociation. And so it's a key word to be aware of. There could be times when it says such and such material disassociates in a solvent, and then you get an idea that it should be an electrolyte. Or I could just use dissolve because dissolve can be used for both electrolytes and non-electrolytes. And then you would have to know if it's an ionic compound going with an ionic or polar solvent that we're going to get some disassociation. Now, since there's three steps going on, then in order for our solute and our solvent to mix, then we have to overcome those first two steps. We have to overcome the energy needed for all of that solute attractive forces to be broken. Sorry, I need the highlight. And for all of those solvent attractive forces to be broken. So we have to overcome that energy. Now, because we are breaking those intermolecular forces, both of those are going to be endothermic. They're going to require us to put in energy. However, the last process, this new solute-solvent attraction that forms after the mixing, that is exothermic because it's a new force being produced. And so that could be the source of some of the energy that we need in order to overcome the solute-solute separation and the solvent-solvent. So this is a diagram kind of showing each of those three steps. So the first one is our solute separation. And so you can see that this is the energy for us to split apart this Cl from this Na. Right? And so it's us breaking up the solute-solute forces. And then for us to find space for those solute particles, we have to spread apart the solvent. We have to split those up. So we have to overcome the attraction between the solvent molecules. And then the last step is we form these solvation shells, or we form these new attractions between the solute that's dissolved and the solvent. Now, in this case, when we had an ionic compound, you can see that this is a dipole over here, and this is an ion. And you can see how they would be strong intermolecular forces that could develop inside of our solution. And this could be one of the driving forces for why our solute can dissolve so easily inside of our solvent to form that solution. Now, the term hydration is sometimes used. hydration is the solvation of the solvation step of making a solution, but this is only when water is the solvent. So sometimes you hear things about this has a hydration energy of this, and that's because it is using water. So it's the surrounding of the solute ions by all of the different solvent ones for water. Solvation could be any type of solvent. Now you can also see that it's possible for more than one of these solvent-solute interactions to form. And that's how we can get stronger, or that's how we can get solutes with stronger intermolecular forces to dissolve inside of a solution, is that instead of only forming one connection between Na and Cl, we can form, in this case, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 of these ion dipole attractions instead. So it is possible to form more than one of these solute-solvent attractions. And so when we think about solutions, remember that like dissolves like, and this means that a solute would dissolve in solvents of similar polarity. So polar ones dissolve in other polar solvents, nonpolar ones dissolve in other nonpolar ones. When we think about that, it kind of makes sense, because in that first step, when we split apart all of that polarity, or this might be when we first split it apart, if it's nonpolar, then we don't need much energy there in order to separate them. But a solvent, if this one is polar, requires a bit of energy to separate polar molecules from other polar molecules. When we reform that solvation step at the end, if we have a nonpolar material and we have a polar material here, there's very little attraction between them, because this can only be London forces, this can only, and so the two that are being held together are just going to be held by those London forces from the nonpolar. That means that in general, this solvent would prefer to stay with other polar molecules in that polar-polar bond as compared to a non-polar polar bond. So even though the solute might gain something from interacting with a polar, because it probably has a stronger force that would develop, the solvent attraction to other solvent ones is stronger and won't be overcome by this non-polar polar attraction. So let's look at this. Right now we're talking about hydration energy. So we have MgCl2 and NaCl, and we want to see which one of them is going to have a higher hydration energy. So hydration energy is that solvation step with water. And so this is when we have our ions interacting with our water molecules. So for magnesium, we would have MgCl minus, and we have Na plus and Cl minus. So if we wanted to think about those ion dipoles, which one is going to have a stronger intermolecular force? Is it going to be with the MgCl2 or the NaCl? And then is a stronger force going to give us more energy or less energy? So if we think about it, an ion dipole, we're looking for stronger attraction. And so magnesium and sodium, one of the big differences is their charge. The sizes are actually relatively similar. And so magnesium is a +2 and Na is a +1. And so magnesium, this ion dipole, is going to be stronger than sodium's ion dipole. The chlorines in both cases are the same, so we don't have to worry about them. And so if it's a stronger ion dipole, then it should have a higher energy. And so we're looking for MgCl2 to be that higher energy. So the overall process has a delta E for that change. Now, that's going to be made up of 3 different steps. It's the change of energy from the solute separation, the change of energy of the solvent separation, and then we subtract from that the change in energy from the solvation. Now, in general, the solute separation should be positive, which should require us to put energy in there to separate it. The solvent separation should be positive, and then our energy of our solvation is going to be a negative because it requires so much energy in order to, or we should be getting that energy back out. Now, overall, if that delta E of that symbol is positive, then the solution will probably not dissolve. If overall the delta E is negative, then the solution will dissolve. So that's how we can use these energies to kind of get a prediction about whether we think it will dissolve or not. So we're going to try that here. So we have our solute separations and our solvent separations, and then we have the solvation energy that we get back. So we want to compare these here. So we can plug it in into that equation that we just had. And what we find out is that the solute separation and the solvent separation requires about 933 kilojoules. We release about 805 kilojoules. And so it's unlikely that this is going to dissolve. The reason why is that it requires more energy for us to separate the solute and the solvent than we get back from making the mixture. So in terms of our energies that we know about so far, it wouldn't make any sense for the solution to form. And it wouldn't make any sense because it would have a lower energy as 2 separate materials than it would have as one mixed together. Now, that doesn't mean that in real life it wouldn't dissolve, because in real life it's a more complicated picture than that. And that's because in real life we have to consider something else, and it's called entropy. Entropy is this desire of kind of like everything to move towards randomness. So entropy, how we define it, it's a function of probability. So as we increase entropy, the system becomes more probable to have that arrangement. So if you were to shuffle your cards, a low entropy arrangement might be that all of your cards would end up black, red, black, red, black, red, all the way through for your deck of cards. That could happen, but it has a very small chance of that probability of that happening. Then a different arrangement where we might have a mixture of blacks and then reds and then blacks and then reds. Now, entropy holds true because the vast majority of things, entropy holds true because objects tend to go from situations of higher energy to situations of lower energy. And so the less random arrangements are said to have lower entropy. The more random arrangements are said to have higher entropy, and higher entropy means that we have less energy. The idea is in order to get to a state where we are in a more ordered or organized state, it requires energy to do that. So if we are organizing our cards to be black, red, then that would be a higher energy state than if we just had a truly random mixture, because it took that extra bit of energy for us to go through and organize them. So entropy is kind of like that movement of things towards that disorder or that higher entropy state. And so what that means is that if there's a choice, our system would prefer to get into a position where we can have more randomness for its energies. So an example of that is dissolving solids increases entropy. A solid is very ordered. That means that it doesn't have many options about where it can be arranged as, but ions have more disorder in that. Our lithium and our chlorine in this picture in particular, those ions can move around in random locations inside the solution, and so we could have a higher entropy compared to where it was a solid where everything was fixed. Now, dissolving solids can be driven by just this entropy side. So that's why when we went back and we look at this, we had to say it's likely that it's not going to dissolve, not that it's not going to dissolve, because there's a chance that if there's enough entropy difference, that entropy can drive that process forward. So this may be enough to overcome a small positive change in energy needed for dissolution is by increasing our entropy. So it can be an entropy-driven reaction. Now, what that means is that overall, most dissolutions are exothermic. However, we can have a few that are endothermic. They just have to be driven by an increase in entropy. One example of this is those instant cold packs that you use in a first aid situation. The instant cold packs, what you need to break and then shake is actually you're dissolving a solid into a liquid. So you're breaking the pouch that the solid is contained in, you're shaking it around to encourage it to dissolve, and as it dissolves, it's a slightly endothermic process. The entropy of the solid dissolving is driving that dissolution forward, and because it requires some energy for that to happen, then it's going to pull in the energy from its surroundings, that is our temperature, and it's going to lower the temperature as it drives that process forward until finally it can no longer dissolve. And so that's how our instant cold packs work. Now that we know how solutions form, we're going to talk about their units for solutions. Now, units for solutions come in a lot of different ways, and so we do need to know these. I'm going to highlight the important ones. So we should already be familiar with things like molarity, but that's going to be coming back, and so we should feel more comfortable with it. We're going to introduce a new one called molality, mole fraction. We also get something that's mole percent. Now, parts by mass can be either our mass percent. It can also be in terms of ppm. You don't have to worry about ppb. We can also think about ppm and how it might be related to volume as well. And so with our concentrations, things can become a bit complicated. So you really want to practice these, which is why we will be doing a problem-solving session where we can practice working on solving these type of problems. So let's look at this, or let's look at these definitions first. So molarities have specific units attached with them. So we get molarity because it's that big M, and it stands for the moles of the solute divided by the total volume of the solution. On the other side, molality is a similar starter. It's the amount of solute in moles, but this time it's divided by kilograms, and it's only the solvent. Now, molality and molarity are very similar, and so we want to make sure that we're paying attention to how they're written and their symbols. One's a big M, one is a little m, so you want to make sure that your handwriting is clear for those. Molality is used much more often when we have changes in temperature going on. That's because molality doesn't change with a change in our temperature, but molarity can sometimes change because materials expand or contract with an increase in temperature. So our molarity is defined as a volume material at the bottom. And so if our solution increases in its temperature, increases in its volume as the temperature goes up, its molarity actually goes down during that process. Its molality would stay the same. So we use molality more often when there's a change in temperature. Mole fraction is just moles of solute over the total number of moles. Mole percent is basically take your mole fraction and then multiply it by 100% to turn it into a percent. Mass percent is the similar way. Mass percent is going to be the mass of the solute over the total mass of the solution. And then you multiply that by 100 in order to get that into a percentage. ppm, you already worked with it for that one lab, but if you don't remember, ppm stands for parts per million. And so that's the parts of the solute over 1 million parts of the solution. So that's everything on the bottom part. So you can do that mass to mass. You can also do that as volume to volume. Both of those will give us a ppms. Now, sometimes what people use is they do it for grams to milliliters, right? And they do a mass to a volume, and they're making their assumption that 1 gram is equal to 1 milliliter when they do that. That's not always the case, but it is when you make a lot of solutions with water, and so that's why sometimes you'll see that made. ppm is very common for dosages in the healthcare field when we're dealing with very small amounts of a solute. So let's try this. What volume of 0.50 molarity NaCl is needed to form 500.0 milliliters of 0.15 molarity NaCl? So we know that we have 0.50 moles of NaCl per 1 liter. And we would like to find a, we would like to form a solution that's 500 milliliters of 0.15 moles NaCl. So if we want to keep our volumes the same, that means that some volume here is going to be equal to 500.0 milliliters. And so we know that their moles are going to be equal to each other. So if we want, what we can do is we can start with our 500.0 milliliters. We can change that into liters. Remember, 1,000 milliliters is 1 liter. And then I'm going to change that into moles. So I'm going to multiply it by 0.15 moles of NaCl, 1 liter. So this is all about the solution that we're going to make. And now that I know how many moles that I need, I can divide that by my initial concentration. And now that's going to get me into liters what volume I need. So I can go through, you can see that my liters cancel, my milliliters cancel, my moles of NaCl cancel. And so we're going to be left in liters of solution. And when we do all that math, it ends up being 0.150. So when you work with your solution parts, sometimes it's important to remember where things are going. So what part will stay the same between the two solutions. And you can also just work on the top part or just the bottom part. It depends on how you go. Now, these next couple of slides go through a little bit more about each of the different topics or the concentration units. So I'll leave those there for you in case you need to review them, right? But molality, remember that's moles of solute, kilogram of solvent. And that's the important part, is it's just the solvent, it's not the solution. A part solution is generally measured in the same one, but we can combine our grams and our milliliters, right? And so these are our ppms. And so when you want to think about them, percentages are parts of solution for every 100 parts total. Oh, sorry, parts of solute for every 100 parts total. Parts per million is parts of solute for every 1 million parts of your solution. Now, for ppm, you can think of it as grams per million grams of solution. It's also milligrams per kilograms. And so sometimes what they do is they mix these two together. We get milligrams per liters because they get this idea from the fact that 1 liter of water is 1 kilogram of water. So for aqueous solutions, they can kind of do this approximation. Now, for a dilute solution, that's fine. For more concentrated ones, it doesn't work out because our solution is going to increase with the increased concentration of the solute. And so for our class, primarily we'll be using ppms, all in grams per grams or grams or liters per liters. We won't be doing as many of these grams per or milligrams per liter, but I just want you to know that that is how that works out, because if you do move into that field, they do show up that way sometimes. Mole fraction is useful because it's comparing moles to moles, and so if we're doing any stoichiometry, mole fraction ends up being quite nice, because then you don't have to go through all the work of changing from a mass to a moles and then moles to moles. You can just use the mole fraction right from the beginning. So we'll do some practice problems. So a solution of ammonia is made by dissolving 35 grams of NH3 in 90.0 grams of H2O. The density is 0.89 grams per milliliter, and so we want to know the molarity of our NH3. So what I recommend with our concentrations is that when we're trying to build them, we want to think about the end unit first and think about the pieces of it. So we're looking for molarity, which is moles of NH3 over the volume of the solution. So now we have two different things that we need to solve for. So sometimes it's easier to solve for the top part and solve for the bottom part independently and then mix them together at the end to get your answer, because there can be a lot of things going on in there and it's easier to keep track of. So let's look at this. The first one that we're going to look at is, well, moles of NH3. That's pretty straightforward. We have 35 grams of NH3. And if we want to get grams to moles, then we need to use our molar mass. So we know 1 mole of NH3. And then we can use our molar mass. We find that from our periodic table. This is 17.03056 grams. And we end up with 2.0551 moles of NH3. So we got that top part taken care of. But now we need to find the volume of the solution. Now, we don't know anything about volumes yet. That's the tricky part. But we do have a density here. Now, density is kind of same for the grams of a solution. This is how many milliliters of the solution that would be. So that's helpful for us. So if we want to figure out this, we could use, well, we have 35 grams of NH3 plus 90.0 grams of H2O. And so this is going to be our entire grams of our solution. And we're going to take that, we're going to multiply it, or not multiply it, we're going to divide it by 1 milliliter is 0.898 grams of solution. And then once we get that, we're going to turn that into liters. So if we add 35 plus 95, or 35 plus 90, that's 125. Divide that by 0.89. We end up with something like 139 milliliters. We divide that by 1,000. That gives us 0.1392 liters. And so if we take those 2.0551 moles of NH3 and we divide that by 0.1392 liters of solution, we should get our molarity. which is 14.76. And so looking at our answers, we should be 15 molarity. And so that's why it's nice to separate them out into our parts and just try to tackle each of those parts independently. Once we have each of those parts, then we can put them together at the end. Sometimes it's easier to do and fewer mistakes than if we try to do both of them at the same time. So when you're trying to convert concentration units, write them as a ratio of one to the other, right? And so you can separate that numerator and the denominator. And then you want to convert the solute part. Then you want to convert the solution part. And then you can put those together. So let's look at this. What is the percent by volume concentration of a solution made by 25.0 milliliters of liquid ethanol and enough water to give 100.0 milliliters of solution? So a percent by volume is going to be your volume of your solute divided by your volume of your solution. And then we want to turn it into a percent. So we need to multiply it by 100%. So as long as our units match up for our volumes, we can just plug them in. So that's 25.0 milliliters. And then our entire solution is 100.0 milliliters. So we're going to be 25.0% by volume. Now, the reason why it's phrased the way that it is because when you mix two solutions or two volumes of liquids together, sometimes their total solution or their total volume is not going to be equal to the sum of their parts. That's because there can be space inside of our intermolecular forces there. And so sometimes those liquids will end up mixing more, and so their volume will go down as your solute might find some open space inside of the solvent. And so our total volume might be a little bit less. It could also be a little bit more if their intermolecular forces are not quite as strong in some cases. And so that's why our total volume can be a little bit different. So you wouldn't want to say that it's really 25 milliliters of liquid ethanol and 75 milliliters of water. You're really just trying to add in as much water as needed to get it up to that 100.0 milliliters total. Now let's look at our mass percent. So we want to find the mass percent of a solution prepared from 15 grams of NaCl and 45 grams of H2O. Now, mass percent is your mass of your solute over your mass of your solution. Now, masses we can add together because we don't have to worry about a change in mass. Us mixing two materials together won't change their total mass. The mass is going to be equal to the sum of its parts. So between NaCl and H2O, we want to think about which one is the solute. So our solute is our NaCl, so that's going to be our 15 grams. And then we want the solution. Now, a common mistake is that people just use the water as that bottom part. But our solution isn't just the solvent. Our solution should be the mass of the solute and the mass of the solvent. So that should be 15 grams of NaCl over 15 grams plus 45 grams, which gives us a total of 15 grams over 60 grams. We multiply that by 100% to get its mass percent. And so we're going to come out with 25% instead of this 33%. 33 is because you didn't find the mass percent. You found the mass of the solute versus mass of the solvent. All right. Now, the last bit that we're going to talk about is going to be our colligative properties. Now, colligative properties are really interesting. Colligative properties are unique for solutions, but what's neat about them is that they aren't dependent on the type of solute particles. It's just about how many. So the value of the property depends on the concentration of the solution, but it doesn't depend on what materials for the solution. So the difference in the value of the property between the solution and that of the pure substance is related to the different attractive forces of the solute particles occupying solvent molecule position. So an example of this is vapor pressure. Now the vapor pressure of a solvent above a solution is always going to be lower than that of a pure solvent. When we think about that, a solution has higher intermolecular forces than a pure substance of it. Well, than just the solvent. Now the reason why is in order for that solute to have dissolved, then our intermolecular forces that we get from the solute-solvent interaction must have been stronger than the solute-solute or the solvent-solvent in relationship. Otherwise, it wouldn't have dissolved to begin with because we needed that energy. Now, its vapor pressure is going to be less because the solute particles replace some of the solvent ones at the surface. And so there's less of the solvent turning into the gas, which is lowering our vapor pressure. So remember that vapor pressure is moving from a lower state, from a liquid state into a gas as those particles break free. So if we put more solute particles on the surface, then we're going to lower that vapor pressure. In addition, basically those solute particles are non-volatile, which means that they're not going to escape. So it reduces the rate of vaporization. So over time, our vapor pressure is going to be lower for that of solutions than it was for that of individuals, of the individual solvent, because of these solute particles and the fact that the solute particles never escape. And so when they are on the surface, then there's fewer opportunities for the solvent molecules to escape. Now, when we think about this, we can think about them in terms of our thirsty solution. So let's say that we put beakers with equal levels of pure solvent and the solution are placed in the bell jar. Now the solvent molecules evaporate from each one, and then they fill up that whole container. So over time, enough particles have evaporated away so that the entire container is filled with the vapor of our solvent. That's what this picture is showing us. Now the liquid level in the solution beaker is higher than that of the level in the pure solvent. This is because over time, because it's got that lower vapor pressure, when our liquids come out from one side into the other, the concentrated solution is going to hold on to those vapors at a higher rate than our pure solvent. It means that when these particles up on top enter into that of our solution, they are going to get stuck more in our concentrated one than inside of our pure one. So they're going to get stuck at a different ratio. Basically, this one releases only a little bit at a time, where this one was releasing more. So over time, we had more particles coming in, we had less that were leaving, and so it's starting to build up a volume there. Now that volume will continue to build until finally the difference in their surface areas would match their rate change. And so this one, our pure solvent, will release less and less vapor because it doesn't have as much material. And this one's going to release more and more because it's gotten more material as it's grown in its volume. So overall, a concentrated solution draws solvent molecules towards it because there's a natural drive for materials to mix. And so if we can mix those, we are going to try to dilute things. So a concentrated solution would draw pure solvent vapor to it. Inside of that is same experiment that we had just walked through. Now, how much that lowers is based off of Raoult's law. So the pressure of the solvent in the solution is related to the mole fraction of the solvent times its normal vapor pressure. Now, the vapor pressure of the solvent is always going to be lower, and that's because our mole fraction is always going to be less than 1. And so we can call this vapor pressure lowering, and we should be able to calculate that based on the mole fraction. So when both the solvent and the solute can evaporate, it becomes a little bit more complicated. We have two aspects that we have to take care of then. We have a pressure for the solute, and we have a pressure for the solvent, and we have to adjust for both of them. But for our class, we're going to primarily focus on this. We're going to be looking at our solvation, or our pressure of the solvent. And so overall, what we would be comparing with is we would take the pressure of the solvent multiplied by the vapor pressure of the solute, or not the vapor pressure, the mole fraction of the solute, and we'll be able to compare and see how they did. Now, ideally, our ideal solutions follow Raoult's law as a straight line. But in fact, the solute is the solute is basically diluting the solvent. So if the solute-solvent interactions are stronger or weaker than the broken interactions, the solution is non-ideal. So in ideal solutions, basically, our solute-solvent interactions is going to be equal to the sum of all the solute-solute and all the solvent-solvent. For our non-ideal solutions, then that ends up not being the case. And so this happens when the solute-solvent interactions are stronger than the solute-solute and the solvent-solvent. And so they're going to be less than expected. We're not going to worry too much about the deviations. You can kind of see them here in the ideal solution. Vapor pressure of B, vapor pressure of A. We're kind of following along on that list. But in reality, you get these curves based on whether you have a strong solute-solute or a weak solute-solvent. For us, what we really want to know is these two parts here. We should be able to calculate the pressure of the solvent using its mole fraction of the solvent. We should also be able to anticipate how much it was going to lower based on the mole fraction of the solute. Now, vapor pressure is one aspect of it, but there's another one as well, and it's called freezing point depression and boiling point elevation. Now, what happens when we go into a solution is we basically increase the area where we will be a solution. We're going to decrease the temperature that we'll freeze at, and we're going to increase the temperature that we boil at. Freezing salt water is a harder thing to do than freezing pure water. Pure water freezes at 0 degrees Celsius. When we add salts, then we kind of disrupt this process. The salt particles dissolve in the water, but don't easily attach to solid ice. So when an aqueous solution containing a dissolved solids needs to freeze, the ice that forms does not normally contain much of the solute. Now, in order for this to freeze the salt water, what we have to do is we have to slow down enough so that way those solute particles can get mixed in with the solvent particles, and then the entire thing can dissolve. Now, what that means is that we get something called freezing point depression. We end up lowering the point that the solvent would freeze in order to compensate for the fact that we have to fit in these salt particles that normally wouldn't have been there. So our freezing point is always going to be a depression. It's always going to go down because it would always be harder for us to freeze it with these particles inside than without them. So the difference between freezing point and freezing point of the solution can be found using this formula here. Delta TF is equal to your molarity times KF. Now KF is not something you memorize. KF is a constant that gets given for that solvent. And so these are examples of them. Now you can see that that KF is in degrees Celsius per molality, right? Remember that this is a small m. So if we look for our molality, remember that that's moles per kilogram of solvent. So let's try a molality one. We can see that in action, and then we'll continue on with our freezing point. So 4.0 molarity of NaOH solution, we would like to figure out its molality. Now we know that it's 1.04 grams per milliliter. And so we're trying to make that transition. So we know that there's 4.0 moles of NaOH inside of 1 liter solution. We know that our molality is going to be the moles of NaOH, but we want 1 kilogram of our solvent. So if I had 1 liter of our solution, we know that that would be 4.0 moles of our NaOH. And now I need to find out, well, what's that mass of that solvent? So if we take 1 liter of our solution and we multiply it by its density, we can figure out how many grams our entire solution would be. 1,040 grams of our solution. Now we can't just turn that into kilograms and put it at the bottom because we want just the solvent, so we have to remove that solution. Luckily, we know that there's 4 moles of sodium hydroxide in there. So if we take 22.989770 plus our oxygen plus our hydrogen, we can find the molar mass of NaOH. We multiply that by 4. And so of this 1,040 grams, 159.99 grams of that is our NaOH. And so we end up with 0.880 kilograms of solvent. And so if we take that 4 and we divide that by 0.880, we get 4.5. And that is going to be our new molarity. And so that's how we can use that for our transition. Now, when we're trying to plug this in for our freezing point depression, this is just telling us the change of it. So if we actually want to figure out when it would freeze, we would have to take its normal freezing point for that solvent, and we would subtract that value from it to find out where the solution would freeze at. So low alcohol is a component of coconut oil, and it's used to make detergents. So a solution of 5 grams of lower alcohol and 0.100 kilograms of benzene freezes at 4.1 degrees Celsius. And so we want to find the molar mass of that lower alcohol. Now it gives us that benzene, its KF is 5.12 degrees Celsius per molarity, and its freezing point is normally 5.50 degrees Celsius. So the first thing I'm going to do is I'm going to find out that difference in its freezing point. So 5.50 minus 4.1. This gives me a difference of 1.4 for my TF. Right? So I know that my freezing point was depressed by 1.4 degrees Celsius. Now, delta T is equal to KF times molarity. So my delta T is 1.4 degrees Celsius. My KF is 5.12 degrees Celsius per molality. And so this is my molality. So if I look at this, my molality must have been 0.2734. And if I know that this is going to be equal to 0.100 kilograms of benzene, now I just need to figure out how many moles of La that would be. So I take that and I multiply it by 0.1. So my moles of La was 0.02734, and that was 5 grams of it. So if I take 5.00 grams, divide by 0.02734 moles, we should get a smaller mass. And it ends up being 182.85, or just about 183 grams per mole. And so that's the useful part about a freezing point depression. On the other side of things, our boiling point elevation, because we have a lower vapor pressure for all of our solutions compared to our solvents, and that's because we put that non-volatile solute in there, then our boiling point becomes higher. Now, boiling point expression is the same formula pretty much as our freezing point one. The only part that we have to remember is that this will always be an increase, whereas our freezing point is always going to be a decrease. So it takes us more energy for us to boil because our vapor pressure is low. And because the vapor pressure is low, then we need to get to a higher temperature in order to get enough vapor pressure to be equal to that surrounding atmosphere. Another caloric property is called osmosis. Now, people always joke that you learn through osmosis, but that's not really what's going on. Osmosis is a very specific term. Osmosis is the flow of solvent from a solution of low concentration to a solution of high concentration. So just like our thirsty solutions, we're always going to flow towards the more concentrated side. What we would like to do is we would like to always be diluting materials. Now, we're never going to dilute them to be pure, but we're always going to work towards diluting them. So we're always trying to make everything a lower concentration because that would be more mixing. So in osmosis, if we were to separate a solution by a membrane that allows for solvent to flow through it, but not the solute, what you'll see is that the concentrated side is going to increase in its volume compared to the more dilute side. As this separates, eventually it will stop because there's enough pressure from one side compared to the other that we won't be able to kind of overcome that force of that pressure. And that's what it means to have osmotic pressure. So the osmotic pressure is directly proportional to the molarity of the solute particles, and then the temperature, and then the R value. So you can use your osmotic pressure. You can use the ideal gas law to kind of determine your molarity of the solution. So we just want to remember that osmotic pressure is happening because we're going from the more dilute or the more concentrated solution. Our solvent is flowing from the dilute solution to the more concentrated one. So we're trying to slowly make the concentrated solution less concentrated. Now, there is a corresponding factor with this, and it's called the Van Hoff factor. Because we're concerned with the amount of particles of solute, the Van Hoff factor takes into account, well, ionic compounds, they don't just dissolve, they disassociate. So if we put in 1 mole of NaCl, inside that solution, we really get 2 moles of particles. We get 1 mole of Na plus and 1 mole of Cl minus. So the theoretical Van Hoff factor is that ratio of the moles of your solute particles to how much you dissolved it. Now, in reality, it doesn't quite match up that way. We don't see a doubling from adding those in. But you can kind of see here that for a non-electrolyte, what we put in is what we measure, right? Because it doesn't break apart, it only dissolves, then they stay together. But when we put in something like NaCl, NaCl makes 2 ions, and so we would expect to see something similar to 2. We won't have to worry about the measured Van Hoff factors. That would have to be something that would be given to you, but you should be able to look at these, and we should be able to figure out how many expected Van Hoffs we would think to see, because we should know A, is it going to disassociate, and B, how many particles is it going to disassociate into. So when we look at this, if we wanted to think about which one is going to have the highest boiling point, well, highest boiling point means the most solute particles in terms of concentration. And so we might be tempted to just have taken whatever concentration was highest. But now we also have to take into account the Van Hoff. So NaCl is an ionic compound, so it's definitely going to be an electrolyte. And so we need to multiply that by 2 because it makes 2 ions when it dissolves. This is a all non-metal compound, so that's going to be covalent. That's not going to disassociate. It's going to be a non-electrolyte, so we can leave that one alone. Aluminum nitrate, well, that is an ionic compound. It's a metal with nonmetals. And so we should take this one and we should multiply it by 4 because each of those aluminum nitrates forms 1 aluminum and 3 nitrates. CO2, covalent compound, we can leave it together. Ammonium chloride, we should multiply it by 2 because it makes 2 ions. And so now when we compare those concentrations, we want to find the highest boiling point, and so now we have an answer that has to be that NaCl, and that's because of the Van Hoff factor. This works the same for freezing point depression. It's why if you've lived somewhere cold or if you've gone to like Tahoe during the winter, the reason why they salt the roads. What they're doing is they're trying to lower the freezing point of the water so that way we don't make ice. Now we use salt because salts are electrolytes, and so their Van Hoff factor can make them go even farther. So if we use sugar, it would also work, except you need to dissolve or you need to shake out twice as much sugar onto the roads than the amount of salt. And so that's why they use salt for when they do these. If we have a more complex salt, so something that makes even more ions, then you would use less of it. Or it would be more effective at driving down that freezing point. You can do the same thing on this one, thinking about which one will have your largest osmotic pressure. Now, since they all have the same concentration, what it's really asking you is who do you think is going to have the highest Van Hoff factor? And that should be our FeCl3. This one, they're giving you the Van Hoff factor, that I, and so they're asking which one is going to have the same boiling point as 0.50 molarity of glucose. So this is 0.50 m times 1 is going to be equal to some concentration times 1.9. So we just need to take that 0.5 divided by 1.9. And so we should be looking at 0.26 molarity. Determine the vapor pressure of a solution at 25 degrees Celsius that contains 76.6 grams of glucose. The vapor pressure of pure water is 25 degrees Celsius is 23.8 torr. So remember, if we want vapor pressure, this is going to be the pressure of the solution is equal to the mole fraction of our solute, or our solvent, times the pressure of our solvent. So this is 23.8 torr. And now we have to figure out the mole fraction of that solvent. Okay, and so now we want to find our mole fraction. So our mole fraction is going to be the moles of our water over our total moles. So we need to take that solute and we need to convert it over into moles. So we have 76.6 grams of it. Now 76.6 grams of glucose. We need to find the molar mass of glucose. So 12.0107 times 6 plus 12 times 1.00794 plus 6 times 15.9994. So we get a molar mass of 180. So 76.6 grams of glucose. 1 mole is 180.156 grams. So we get 0.4252 moles. Now, we want to add to that our moles of our water. So we have 250.0 milliliters of water. There's 1 gram of water for every 1 milliliter of water. And that's 18.01, oh, wrong side. Our molar mass of our water is 1 mole. And it should be 2 times 1.00794. 18.015 grams. So 250, divide that by our 18. We get about 13.877 moles of H2O. So we get 13.877 divided by 14.302. All I did there was I added my moles of my H2O and my moles of my glucose. So we get a mole fraction of 0.970. Multiply that by 23.8 torr, and we get something like 23.1 torr. So that's how we solve those. So you do want to practice with your solutions. There are a lot of different pieces to go through. There's 3 more challenge problems here that I want you to practice, and we'll go over them on our next class where we'll solve some of these solution problems. But work on your different types of concentration units, and then start to work on your colligative properties as well. There you go.